Hello everyone, hope you all are well. These notes are going to cover the second half of Unit 6, Part C. We're picking up with the common ion effect, and we're going to start with how the addition of a common ion affects the position of the equilibrium. And it's basically all about Le Chatelier's principle. So if we look at the following equilibrium, barium chromate, dissolving into barium and chromate ions. If you added barium chloride, it would shift the equilibrium to the left. Why? Because the barium is a common ion. So if you've got a beaker full of barium and chromate, you added to it some BaCl2, you're essentially adding barium ions. So if you add something to your product side, it will cause a shift to the left, and it will reduce the solubility. It will suppress the ionization. The addition of a common ion suppresses ionization. pH can also affect the solubility. Let's take a look at the equation below. Now remember, a high pH means you have a greater concentration of hydroxide ions, and a low pH means you have a greater concentration of hydronium. So the question is, would magnesium hydroxide be more soluble in acidic or basic conditions, and why? So if you add a base, you'd be adding hydroxide, and you'd be shifting the equilibrium to the left. You would be decreasing the solubility. However, if you want to increase solubility, that means we're looking for something to shift it to the right, towards the generation of more aqueous ions. So adding H plus hydronium or decreasing the pH would shift this reaction to the right. Let's try to understand why. Let's look at the reaction. If you added acid or reduced the pH, you're essentially adding hydronium, which is H plus. And the hydronium will react with the hydroxide ions according to the following reaction. So essentially, by adding acid or reducing the pH, you're removing the hydroxide ions, shifting to the right. You're creating more aqueous ions, you're dissolving more of the solid, therefore increasing the solubility. Let's apply the concept of common ions to a more quantitative problem. We want to calculate the molar solubility S for barium chromate in a solution of a 0.1 molar barium chloride. Barium is your common ion here. We're going to compare this common ion solution to a saturated solution that did not originally contain a common ion. So we're going to set up our equation. On our race box. Who cares about the solid? We've already got 0.1 molar barium. See? 0.1 molar barium. It's already in there. No chromate. Minus S plus S plus S. 0.1 plus S and S. Let's write our KSP expression. KSP will be the concentration of your barium ion times the concentration of your chromate ion. And the value for the KSP is given. It's 1.17 times 10 to the negative 10th. We plug this in, we get 0.1 plus S times S. Now, because S is going to be very small compared to 0.1, we can assume that it's negligible and we're going to eliminate it. So let's rewrite this. And we can solve for S, and we get 1.17 times 10 to the negative 9th molar. That's the solubility of barium chromate in a solution that already has a 0.1 molar barium ion concentration. So let's compare this to a saturated barium chromate solution. You see how the solubility with the common ion has gone down? Again, the presence of a common ion suppresses ionization because it shifted the equilibrium to the left. Let's take a look at another problem. This was exercise 5 in your notes. We want to calculate the solubility of calcium fluoride in a 0.025 molar sodium fluoride solution. So we're going to write our reaction. Rice box. Who cares about the solid? Now what's our common ion? It's fluoride. And sodium and fluoride are 1-to-1, so that means that we have a 0.025 molar fluoride already in there. This is plus S plus 2S, S 0.025 plus 2S. Let's write our KSP expression. Don't forget the coefficient becomes the exponent. KSP is given 4 times 10 to the negative 11 equals S. And then 0.025 plus 2S. Don't forget the exponent there. Because S is going to be small, we can assume that it is negligible. We use our simplifying approximation, and when we rewrite this, we get 4 times 10 to the negative 11 equals S times 0.025 squared. Now you can solve for S, and you get 6.4 times 10 to the negative 8 molar. Now we're going to determine the direction of an equilibrium shift by comparing Q to K. This is all about trying to determine if a precipitate will form based on the concentrations that are initially present. So we want to determine if a precipitate forms based on the concentration of the ions that are present and what are required for that precipitation. Remember, a solid, let's take something like Mx, giving M plus aqueous ions and X minus aqueous ions. This equilibrium is at your saturation point. So if you have more moles per liter than what the solution can hold, it will precipitate. That would be a supersaturated solution. And if you have less than what the solution can hold based on the solubility, then a precipitate will not form. So the steps that we're going to take, right, I know they're listed here. I'm going to read through them, but I'll walk through each one as we go. You're going to determine which product is the precipitate. Write the KSP expression. You're going to calculate the concentrations of each ion, substitute these into your Q expression, And then we're going to compare Q to K and determine whether a precipitate will form. So when we do our Q to K analysis, if Q is greater than K, remember the alligator is biting Q, so we're going to follow the direction of the alligator. That results in a shift to the left towards the solid. That means a precipitate will form. If Q happens to be less than K, we're going to shift to the right, and there will be no precipitate that forms. So that's the idea in a nutshell. Let's take a look at a problem. All right, we've got 5 mils of a 0.3 molar lead nitrate, and we're going to mix it with 10 mils of a 0.15 molar sodium chloride. Question states, will a precipitate form? We're going to explain the observations by calculating Q and compare it to the KSP value. So the first step is we have to write our reaction to see what the precipitate is. So we have lead nitrate being mixed with sodium chloride, and you're going to get PbCl2. It's going to be your precipitate. Solubility rules N and A. No we balance. This problem doesn't really matter. Okay, so we know that this is going to be our precipitate. Now, based on the concentrations, after we mix these two solutions, we're mixing them, we're going to determine if this precipitate forms. So the equation that we're considering now, the equilibrium that we're considering, is as follows. Raise our KSP expression is the concentration of the lead ion times the concentration of the chloride ion squared. So what we've got to do here is calculate our concentrations of each ion before I can plug it into my Q expression. And my chloride. We're going to use M1V1 equals M2V2. So your lead concentration was 0.3 initially. We had 5 mils. We need the new concentration, our total volume of 15 mils, because I added 5 plus 10. M2, which equals your lead concentration, is equal to 0.1 molar. Let's do the same for the chloride ion concentration. We have a 0.15 molar, and it was originally 10 mils of that sodium chloride. M2 is going to be the new chloride concentration, and V2 is that new total volume. So M2 here, the new chloride concentration after mixing is 0.1 molar. I've got my new concentrations. I'm going to plug this into my KSP expression. But instead of calculating KSP, I want to calculate Q. So Q, written the same way. We don't know if we're at equilibrium or not. It's going to be 0.1 times 0.1 squared. And Q equals 1 times 10 to the negative third. All right, let's compare Q to K. So Q, K. So Q is 1 times 10 to the negative third, and K was 1.7 times 10 to the negative fifth. Q is greater than K. The reaction is going to shift to the left, towards the solid. If it's shifting towards the solid, a precipitate will form. All right, you can try this one if you want. You can pause the presentation and try it. If not, just keep listening. So we're going to mix barium chloride and sodium sulfate. And our precipitate is going to be barium sulfate plus sodium chloride. And we're balanced. Okay, so precipitate is all I care about. And the equilibrium of interest is the barium sulfate in equilibrium with the barium ions and the sulfate ions. The KSP expression for this is barium sulfate. So remember, where we're heading with this is we need to calculate the new concentrations of each of the ions to get Q to compare to K to determine what direction the equilibrium shifts. And that will tell us if a precipitate forms. Now remember, the total volume, when I'm doing my M1V1 or V2, will be 100 because I'm mixing 50 mils with 50 mils. So your total volume, remember, is 100 mils. Let's calculate the barium concentration. We're going to use M1V1 plus M2V2, and we get 0.2 times 50 mils is going to equal M2. And my total volume is 100 mils. When you solve for M2, you get 0.1 molar barium. And when we solve for our sulfate ion concentration, M1V1 equals M2V2, we're going to use that original 0.3 molar, 50 mils. M2 will be the sulfate, and we have 100 mils. So your M2 is going to be 0.15 molar sulfate. Alright, so we have to find Q next. Remember, the Q expression is written the same as your KSP, but we just aren't sure if we're at equilibrium. You can use initial concentrations for Q, or anytime you're not sure. So that equals 0.1 times 0.15, and Q equals 0.015. Now let's compare Q to K. Q is 0.015. K was 1.1 times 10 to the negative 10th. That was given up top. We can see that Q is much larger than K. The equilibrium will shift to this is the equilibrium we're looking at here. It's going to shift to the left, to the production of the solid. That means a precipitate will form. Alright, that's that. Alright, the next problem we're going to look at is a little bit different. This is an actual old AP question from our free response. I forget what year it was, but let's take a look. Let's try to understand what's happening. We have a solution that contains 0.02 molar fluoride and 0.1 molar sulfate. So what we're trying to find here is what is the concentration of strontium that's going to require to precipitate each of these salts, the strontium sulfate and the strontium fluoride, and then which one precipitates first. So we have two equilibria that we're going to be considering once the strontium has been added to the solution. We have that strontium fluoride that will precipitate, and we have the strontium sulfate that will precipitate. The KSP expression for each of these. So we have our strontium, we have fluoride, here's our strontium, and the sulfate concentration. All right, so the given information here, the KSP values, and the given concentrations are going to allow us to plug numbers into the KSP expressions and solve for the strontium ion concentration. So let's start with the strontium fluoride. The KSP from above with 7.9 times 10 to the negative 10th. Remember, we're looking for the strontium concentration. It gets us to that saturation point, right? Gets us to the equilibrium between the solid forming and the aqueous ions being produced. And the fluoride concentration was what? 0.02. When you solve for the strontium concentration, you get 1.98 times 10 to the negative 6. That's roughly 2 times 10 to the negative 6 molar. So this number is telling us this is the concentration of strontium that needs to be added to form a precipitate. Let's solve for the next one. Using the KSP given for strontium sulfate, which was 7.6 times 10 to the negative 7. Again, we're going to solve for the strontium concentration. The sulfate ion concentration was 0.1 molar. Solve for strontium, and you get 7.6 times 10 to the negative 6 molar. So what this means is, this is the concentration of strontium that's required to precipitate the strontium sulfate salt. So let's look at these two values to determine which precipitates first. The one that requires less strontium will precipitate first. So 2 is smaller than 7.6, which means strontium fluoride requires less strontium, it's a smaller number, to precipitate the strontium fluoride salt. Next, we're going to discuss selective precipitation. So, ionic salts that share a common ion will require different concentrations of that ion to form a precipitate. Each salt has its own KSP value. As a result, ions can be removed selectively. The key here to solving all of these problems is by looking at the KSP values. you need a few orders of magnitude, meaning powers of 10, to be selectively precipitated. The bigger the difference in the KSP values, the better the separation. So let's say you've got a beaker that has cadmium ions and lead ions. You want to selectively precipitate them. The reason you might want to do this is to remove one ion while leaving the other dissolved. It's a separation technique. So what are we going to add? We can add oxalate, or we can add sulfide ions. Now, what we're looking for is one compound, the cadmium or the lead, to form precipitate and the other ones stay dissolved. So a large difference in solubility or a large difference in KSP values is going to help us to identify the best thing to add, either oxalate or sulfide. So let's focus here on these two, the cadmium oxalate and the lead oxalate. Notice the KSP values. Now who cares about this number here? Whatever. Just look here, 10 to the minus 8th versus 10 to the minus 12th. That's 4 orders of magnitude difference. Now, if we look at the sulfides, that's only 1 order of magnitude, 27 versus 28. So the greater the difference in the KSP, the better the separation. The more orders of magnitude you have, the better the separation. So if you wanted to selectively precipitate one of these ions, the best thing to add would be oxalate. So which one would precipitate first? Well, the lead oxalate has a much lower KSP value, which means the concentration of oxalate required is less than the concentration of oxalate required to precipitate the cadmium. So the lead oxalate will precipitate first, leaving the cadmium ions behind in solution.